Hey there, in this recording I am going to describe in the pi space physics theory a very fundamental physics formula which was discovered by Daniel Bernoulli in the 1700s, if memory serves, and it's to do with the behavior of fluids, and two properties of fluids two properties that he discovered that seems very counterintuitive, and we know it's true because experimentation has shown that it's true, but it's always difficult for people to understand how it works. And stated very simply, it's Bernoulli's law. It's to do with velocity and pressure, and this is one of the foundational formulas for aerodynamics and the way fluids behave. And it's to do with the properties of fluid, namely the velocity of a fluid and the pressure of a fluid. Now, we know from Pascal's law that we can manipulate the pressure of a fluid through hydraulics, but what Daniel Bernoulli studied was to do with these two properties, namely velocity and pressure. Now, this lecture is taken from a document which is called the Quantum Theory document, and it's a PDF and HTML, and it can be found on my blog on pispace.blogspot.ie, and it can also be found on archive.org, and it is part of the Quantum Theory document and formulas. So the section that I'm going to cover is in that document, and it's called Bernoulli high velocity and low pressure. Now, in a classical sense, it's taught in the following way. What we do is we find the average, the kinetic energy, the average velocity. We divide v squared by 2 to get the energy, the average energy. We add the gravitational constant, Gz, and we add the pressure, or the density of the object. But it's the pressure over the density. It's to give the unit pressure. And what Daniel Bernoulli found through experimentation and formulated it was that the velocity and the pressure are always constant. Now, that seems very logical, that it's an energy constant formula, and what it essentially says is that if the velocity increases, the pressure drops. So, in other words, if we create an experiment where we see a narrowing of a tube, for example, a fluid and a pipe, and what we do is we narrow the tube here, and we see that the pressure drops and the velocity increases. So you have higher pressure here, lower pressure, and then the fluid speeds up. So what we find is that it seems counterintuitive. One would imagine that when a fluid goes through a compressed area, you would imagine the pressure would increase. But what we find is that the pressure decreases, and we can show the formula to prove the point. But I think it's pretty clear to most people that it is counterintuitive why that happens. But you can argue from the formula that it makes sense because energy is conserved, and we know it's true because when we experiment, we can see it happening. And we know, for example, with a plane wing, where we have compressed streamlines, we have a change in pressure, and then the plane wing moves in that direction. So what I'm going to do in this lecture is I'm going to describing it in using PySpace, why it happens and why it makes sense. I'm going to try and sort of show it's intuitive as opposed to counterintuitive. Now, in the document that I've developed, I have this notation I developed. It's pretty simple. It maybe looks a little bit complicated here, but it isn't really. I have a local and I have a non-local description of this formula up here. So you have this formula which has gravity, it has velocity, and it has pressure. And if you come down here, this formula has two Hamiltonians, a local one and a non-local one, and all that a Hamiltonian means is that if you change the energy in a Hamiltonian, the total energy change is zero. That's all it really means. It's conserved. So what this is saying is that we have a local water particles or fluid particles which have pressure, and they have a wave function. Yeah. So what we do is we extend the whole notation regarding fluids, and we include a wave function. And this piece here is just the cos arc sine part is just the kinetic component. And so if we have a change in pressure, we have a change in the kinetic component here. That's all that says, and that's local. And by local, I just mean they're the local particles of the fluid. Now, those particles exist in this non-local part. Those particles exist inside a field, a gravity field in this case, which is here. And you know, it's all to do with the amount of the gravitational constant, the amount of mass, and then r squared, which is the radius squared of the area of the object in question, producing gravitational field times h. So it's g times h. That turns out to be a gravitational constant times h divided by c squared in this case, times wave function. So in other words, we've got a gravity field here, got a gravity field here, we've got a gravity field here due to mass, and then we have this other piece here, which is just like over here, and it just means that you have the kinetic component. In other words, if you're inside a gravity field at a certain position, there's an associated kinetic component. So the kinetic energy and the potential energy are the same, and we multiply the total expression by the density of the fluid. But all that's really trying to do is, this is just trying to represent this, right? In other words, a velocity component which has a kinetic component, a potential component, and a pressure component, and that's all that is. So this is the pressure component, which has an associated kinetic component, which is local, which is the particles, and then we have the fields, which is characterized what I call non-local. In other words, you're inside it, and it's generated by mass and the gravity constant, and it also has a kinetic component, which is the kinetic energy, times the density. That's all that's trying to do. It's just trying to represent the same formula in a different way. Now, the advantage of this notation, I think, personally, is that it also includes a wave function, right? So in other words, we learn a lot in physics that every particle has a wave. You know, there's a wave particle duality in reality. This formula tries to spell that out. So if you alter the gravity component, you alter the wave component, and so a change in velocity alters the wave function, a change in the gravity field changes the wave function, and a change in the pressure changes the wave function. That's all that says here, and it's with respect to time. This is based on the Schrödinger approach to waves. So it's pretty straightforward. It's a Hamiltonian, two Hamiltonians, and they sum up to the same result, which is a constant. So that's all that's saying. It's my own notation. The star just means that they're multiplied against one another. which is like the complex conjugate in quantum mechanics. But essentially that they're just representing the different aspects of a fluid in terms of the wave function and so on. So, for the purposes of the discussion, where we have this here, what I've showed you up here, we have high pressure coming in, it goes through a narrow tube. You would imagine it should have even higher pressure, but it doesn't. But it goes faster and the pressure drops. So we can see that it's all at the same distance in gravity. So we can drop the gravitational part of the expression, which is this part here. So the expression simplifies to just one Hamiltonian, which is a kinetic component. That's all that this here means. In other lectures I've described this. If you're unsure, it's in the document if you're unsure. But just think of this as kinetic energy here, and then this is the pressure component, both of which have a wave function. So all that really means is when you look at this function here, we're dropping gz. That's all we're doing, right? All right, that's all we're doing, right? So that's all that we're saying here is we're saying pressure and the kinetic component are constant. Now, what we do then is we start talking about the wave function as opposed to just the fluid. So we imagine the fluids moving through with streamlines, and the streamlines all come in together here, and the particles of the fluid, come in here, and you get low pressure. Now, in this case, I express the streamline, which is these series of particles here, as essentially just a series of particles. But you can also describe them as in terms of like a wave function, as I've shown here in this diagram. So all that I'm describing here is this part of the expression here, the wave function part, just here, this part here. That's all that I'm trying to draw here. So this is like the wave function, and this is the streamline, and the particles all push against each other, so they have some kind of pressure. Now, the next point to make is if we need to map excuse me, we need to map pressure to these what I call pi shells. They just mean atoms, and they have different sizes. So if you move faster, the atoms get smaller, and if you move slower, they get bigger. But how does that work in pi space? In terms of atoms, in terms of fluids. So if you have a higher pressure, what we actually say is that maps to a change in the size of the actual fluid particle or atom. So if you have higher pressure, you have a slower velocity. So it's a larger particle. And if you have lower pressure and you have higher velocity, lower pressure means that the atom gets smaller, and the velocity, but it moves quicker because the wave function is more compressed. So you can see if something gets smaller in pi space. Now the change in actual size of a particle of a fluid moving through a compressed region, the change is quite small. It's quite minimal. It's actually not. It's actually relativistic. It's a 1 over c squared calculation in terms of the diameter, so it's quite small. But this is just for illustration purposes, to sort of show that the particle gets smaller. So in other words, if we have a high pressure particle here, it's basically a larger particle and a larger wave function, and then as it goes in here, all the streamlines compress, and then the wave function here becomes smaller, and then the particle becomes smaller. So essentially what we have is so this is what the pi space formula tries to call out, is that the wave function is actually altered when it passes in through a confined space, and it actually the wave function compresses in here. So it's the wave function that gets compressed in here. So you have larger all these wave functions all going into this smaller area, and they compress. And then to conserve energy, the wave functions become smaller, but their period increases, and it makes the particle smaller by a small amount, and it moves more quickly. So this is how we see this whole wave particle duality in pi space. We see a particle having an associated wave function, and if you compress the area that it goes through, you also alter the wave function. So this is why it's more intuitive in pi space to sort of think of the Bernoulli example. In other words, if you think of a fluid as a series of wave functions that come in here, the wave function energy must be conserved. Therefore, you get a shorter wave function in here, a shorter one, such as drawn here, compared to this one. The particle becomes a slightly smaller in terms of its diameter, and therefore it moves faster. Now, if you've studied the pi space theory, I've shown in other lectures that the smaller that an atom becomes, the faster that it moves. The larger that a particle is, the slower that it moves, and the larger the wave function. Therefore, if you have a fluid coming in here, the wave function gets smaller, but the velocity of the particle gets larger. And if you want to call that out as a formula, I'll just go back up. This is the way we describe it. This is the associated wave function here with regards to, for example, the pressure. So this wave function here and this wave function here, the kinetic wave function and the pressure wave function, they sum up to be a constant. So the way pi space would explain it is, it's not just that the velocity and the pressure are constant, it's also that the wave functions are constant. Yeah, the wave functions are also constant. So in other words, typically in physics you describe them in terms of Hamiltonians. So that's it. It's very intuitive. So you can make something move faster when you compress where the wave function is. And the only other point I'd like to make, just for clarity, is the wave functions associated with the moving fluid are contained within the containing object. In other words, like a pipe, a glass pipe, metal pipe, whatever. They stay inside the confines of the containing object. In the same way that if you have food in a cooker and you turn on an oven, the heat for the most part stays inside the oven. The wave functions, and we know that in physics that the thermal quantum waves stay inside the oven, and they have distinct wavelengths based on the size of the oven and the temperature and so on. But so in pi space we call out the pressure in this way inside a fluid. So the pressure is also expressed in terms of a wave function as well as velocity and pressure. And just very finally, pressure has a wave function here, and then real quick, just final, higher pressure, slow velocity, and this is the larger streamline amplitude, larger pressure, and then lower pressure, higher velocity, smaller streamline amplitude, lower pressure. We add the wave function, we call that the wave function explicitly, and in theory, I think, according to the theory I've developed, it makes the Bernoulli formula more intuitive. Even if you choose to stick with this formula, and you have Bernoulli, high velocity, low pressure, if you can even just kind of visualize the wave functions shortening and lengthening because of the wave and the particle behavior, it hopefully should mean that when you have this what I think of as a counterintuitive description through this function, through this formula, it becomes more intuitive. That's it. Alright, I hope that helped. That's it for now.